In this presentation, we're going to talk about stochastic compartmental models, which are models that add an element of randomness or stochasticity to the deterministic compartmental models we've already discussed. So the reason for this is that deterministic models can result in fractional units. So these often don't make sense biologically. So if you think about half a sick person, or the attofox, which is an example from ecology, which is 1 × 10 to the negative 18th foxes, these aren't units that exist in the natural world. In a large population, this might not matter. So for example, 0.0001% of New York City is still about 20 people. So you can get very small fractions, but those still have biological meaningness. This is much bigger of a deal in small populations, where you start talking about the difference between 0 and 1. This is also a big deal in large populations when you're talking about extinction or emergence, when the number of infected people you have is very, very small. So, if you are down to, even if you're in New York, the difference between 1 case of COVID and 0 cases of COVID is a big deal. If you're in New York, the difference between 0 cases of smallpox and 1 case of smallpox is a very big deal. And so this can apply both to small populations and the very beginning and very end of epidemics, even in large populations. And the reason for this really is driven by the idea of stochastic extinction, which is the extinction of a disease due to randomness. So this is when, in an SIR model, your I category equals 0. Transmission stops. You're now at what's known as a disease-free equilibrium. In a deterministic model, this can be essentially impossible. There will always be some infinitesimally small population of infected individuals who can reignite an outbreak given enough time and a large enough pool of susceptibles. This can have very large consequences for planning. So for example, when we have models that add births, we see these periodic fluctuations, these sort of oscillating epidemics that take place over time. Those only make sense if the disease hasn't actually gone extinct. If there is some potentially very, very small but existent pool of infected individuals who can still transmit. There are some other aspects to this though. So in this particular case, R naught greater than 1 doesn't guarantee an outbreak. It merely makes it more likely. If you think about sort of the noise in an R naught estimation, if you say 1.2, that says on average, an infected case causes 1.2 cases. But if that's 0.9 cases in this particular case, or in this case 0, you don't get an epidemic. The epidemic dies out even though R naught is greater than 1. Similarly, R naught of less than 1 can still cause enough cases that we might view it as a public health problem. Some of my own research sort of suggests that a lot of hospital-acquired infections and the epidemics that emerge from them actually aren't epidemics. They're sort of small, self-limiting, R naught less than 1 events caused by an introduction event, but that these happen enough that it looks like an endemic disease. So this can create a public health problem even though R naught is less than 1. You can't sort of drive R naught less than 1 and say, okay, we're good, let's call it a day. And this can also induce a great deal of uncertainty into the system just due to random chance. So this is a model I've worked on with some colleagues on vaccinating dogs in Kenya against rabies. And this is essentially, I believe this is 1,000 simulations of the same vaccine campaign. So this is essentially a periodic vaccine campaign where people come by, we try to vaccinate as many dogs as we can. And the question is, how long will it take for us to get to disease-free state until we have no infected dogs? And the answer to that is we start seeing sort of epidemics that reach there and get there a little over 500 days. But then there are still some simulations that have epidemics out to about 1,800 days. 1,800 days. So this is, if you're talking about a planning campaign, how long do you need to sustain this campaign is actually very, very wide. And so we can think about this from the perspective of something like a survival analysis where we treat each of these simulations as a data point and say, okay, what proportion of simulations have successful elimination? And again, we can start to see that early on you have sort of most epidemics keep going until about 750 days. That's where we start seeing rabies start to be eliminated. But really, if you get to the 50% mark for this, it's out until about 1,250 days. And again, there's about probably 5% of our simulations aren't done after 1,800 days. So again, how do you plan for this? How do you fund this? How can you tell if you failed? If your campaign isn't working the way the model is suggesting, this all becomes a problem if you have random noise. So a question that often comes up from this is, okay, how small is too small? So this is something of an open question. There's a lot of sort of obviously type answers. So the city of New York is a large population. The United States is a large population. An 18-bed intensive care unit is a small population. But an entire hospital is also a small population. They're still subject to stochasticity. Is the average college town, so I live in Pullman, Washington, it's about 35,000 people, is that small? What about a small city? So a city of, say, 500,000 people, is that small or not? The answer is, well, it sort of depends, which is the epidemiologist's favorite answer. In my case, my opinion is if you're working in most animal and wildlife systems, you're almost certainly working with a small population. And for other populations, it's probably worth checking. So you can often implement a simple model, just a very basic SIR model, run it both stochastically and deterministically, and see if it matters. And if it doesn't really matter, then that's not maybe something you need to worry about. So in terms of implementing stochasticity, there's a number of different ways to do that. You can use what are called stochastic differential equations. These are similar to ordinary differential equations, but they add a random noise process. These have many appealing traits to mathematicians, so you get nice analytical solutions and things like that, but these are well beyond the scope of this workshop. What's much more commonly used is various stochastic simulation methods, which is what we're going to cover. But in order to cover that, the first thing we really need to understand is random numbers. So stochastic models use tremendous numbers of random numbers. And how random number generators work is, generally speaking, there's some process on your computer. So for example, the 6th or 7th or 100th digit of your computer's clock, and your computer grabs that, runs it through an algorithm, and that generates a random number. That's what's called a pseudo-random number. It works perfectly well for our purposes. If you are a spy or a bank or a casino, it doesn't, but that is, again, something that's sort of well beyond what most epidemiologists are worried about. But this also introduces the notion of what's called a seed, which is something that you may encounter in a lot of code that's stochastic simulations, where you do something like, in Python, it's set.seed. I don't remember what the command is in R. It's probably just seed and then the function. And what that does is that says, instead of grabbing that number that's sort of coming out of a random stream from your computer, take this number as the thing you do instead. So for example, if you give it, 1, 2, 3, 4, it will always start at 1, 2, 3, 4, and it will generate the same stream of random numbers. So this is really nice for what modelers sometimes call V&V, or verification and validation, which is where you're trying to make sure your model is working. You're trying to make sure that it's giving you the right answer when you're giving it sort of a known thing. And during those processes, during the debugging process, you don't necessarily want your answer to keep changing because of randomness. You want your answer to only change because of things you've changed within your model. So you can use a seed to make sure it's reproducible. This is also true if you're publishing your code and you want people to be able to exactly reproduce your results. You need to fix your seed so that people are using the same random numbers you are. So when we talk about the analysis of these models, we're going to sort of talk about how to handle these models before we talk about how to do them. If you think about this, every time you change a parameter, you're creating a new counterfactual scenario. And many and most of these simulations are very amenable to basic statistical tests, because in that case, you don't have confounding. The difference between your simulations is just what you changed in your parameter, so you can get away with things like t-tests or ANOVAs. The caveats to this are that p-values don't mean what you think they mean. Even for epidemiologists who generally don't speaking trust p-values, you should sort of double plus not trust p-values here. And then you should plot all your data at least once. Multimodal, non-normal, and distributions like that are quite common, which may mean you need to use the sort of non-parametric equivalents of things like t-tests or ANOVAs. So on the topic of sort of p-values and sample size, let's talk a little bit about why simulations worry about sample size. The reason simulations worry about it is what's called the law of large numbers, which is that the results of a random process will approach its expectation given infinitely many simulations. So this means, because in many of these models we don't know the expectation, what we're doing is we're essentially simulating it until we get enough samples that it'll tell us. So a very simple example of this, if we didn't know the probability of a coin coming up heads, and we just flipped it once, it's either 0 or 1. And we have to flip it a lot until we start getting actually to 0.5 as an answer. And given infinitely many simulations, we'll get it to 0.5. So you can sort of see that on the graph, that it sort of wildly is pretty inaccurate for a while. And it takes a good 60 or 70 coin flips before you start converging on the actual answer. One thing we don't really worry about for sample size is statistical power. The goal is to converge to an answer and minimize the impact of random numbers, not necessarily boost statistical power. The reason for this is while p-values are dangerous at the best of times, for an observational study, study power is essentially a function of your sample size, your effect size, your test, and alpha. So your test is usually fixed. There's usually an appropriate statistical test that you should be using. Alpha is fixed, generally at 0.05. Your effect size is whatever it is in your population. You can't really control that. And so all you can do is tinker with your sample size. So that's where you start trying to get study power. But sample size is hard to increase. You have a limited source population, recruitment is hard and often expensive. In a simulation study, that's all still true, but now think about what determines your sample size. Your sample size is a function of computing power and patience. Power is now something that's trivially modified by the researcher. You can throw your simulations on a cluster and have, hundreds or thousands of computers all working on your code at the same time. You can do cloud computing, and you can just pay Amazon for new computers to do your thing. Or you can just go ahead and take a 3-day weekend and come in on Tuesday and see how well your simulations did. So an example of this is a thing I was working on I simulated a true difference in this model, but it's one that shouldn't matter to epidemiologists. So in this group, essentially the difference between these two models is that the high-risk group has a relative risk of 3.37 versus 3.3701. And I picked this because this is sort of 2 significant digits past where most editors of journals like Epidemiology or AJE would tell you drop that level of precision. It's not real. So all it took to get a significant difference between these two models is 100,000 runs. This averaged 3.37 seconds per run. I swear that wasn't fixed to the relative risk. It just happened to be that way. There are 4 processor codes on my computer, and I wrote this as sort of multi-threaded code. So that's 250,000 runs per core. That means this took about 7 hours. All of that was overnight. I hit run, I got up, and went home. And so this could have even been shorter if I was fishing for answers. If I had my simulation check when I hit P of 0.05 and stop the moment I got a significant result, this could have been much shorter. So essentially the answer for can you get a significant result from a simulation is how expensive is your computer and how long are you willing to wait. And so really p-values are sort of a meaningless concept here. Now, moving on, how do we actually do these models? How do we simulate these models stochastically? One of the most common methods is Gillespie's direct method. This was originally created by Daniel Gillespie, who was a computational chemist. And this is an exact stochastic simulation of an ODE-based compartmental model. So basically you take the standard compartmental model we've talked about, and we make a stochastic simulation out of it. There's faster approximate algorithms available. We'll talk about those in a bit. What this does is this converts rates to probabilities, and then it treats individuals as indivisible. So these are now integer valued units. Importantly, this scales very poorly with population size. So essentially, as your population gets bigger, the time between events gets smaller, and that means you have to run more sort of iterations of this algorithm. Now, how the algorithm actually works is very straightforward. So essentially what you do is you generate the time until the next event. So if you're at time 0, you will generate how long it will take until an event occurs. So say it's 1 hour. You advance your, you decide what event is going to take place there. So you take the sort of weighted probability of all your events and you determine which event takes place. You move up to that time point and then you update the compartments with what happened. So we'll use an example of this. First, converting rates to probabilities. This is a pretty direct translation. So if something happens every 2 days, the probability of having it in a single day is 1/2. So if we think about 2 events, one takes place every 2 days and one that takes place every 4 days, an event takes place every 1.33 days. So what we do is the algorithm would say, okay, advance our time 1.33 days, and then we need to randomly determine which event happens. So here we draw an event randomly, weighted by the frequency with which those events occur. So for example, the event that takes place every 2 days will happen twice as likely as the event that takes place every 4 days. So 2/3 of the random draws will be event 1, and 1/3 will be event 2. This means that events that happen more frequently are more likely to happen, but this is not guaranteed. So you essentially randomly generate a number between 0 and 1. You look up on a table which event that is. That's the event that happens, and then you update your compartments. So if that was somebody moving from S to I, you take one person from S and you move them to I. And this is the big advantage of the Gillespie algorithm and many stochastic methods, is the treatment of compartmental populations as integer valued. An event occurred. Somebody moved from one compartment to another. It's not this continuous, instantaneous process. So it's useful to think of these as a list of transitions. So how someone moves from S to I, how someone moves from I to R. And so sort of conceptualizing that way. And there's a paper I've written where instead of equations, we give a table of transitions. This is what this ends up looking like. As you can see, this is a model of an ICU. And what we have is these very jagged lines. So this is, if this was in a deterministic model, these would all be straight. These would be curves where this is at endemic equilibrium. But instead we get these jagged lines as we have events that take place. These are mirror images of each other because there's only two states that each individual can be in. But again, you get this sort of random noise. So the other algorithm we're going to talk about is what's called tau leaping. As I discussed, Gillespie's direct method is an exact method. It gives you a statistically valid realization of a particular stochastic process. But it's very computationally intensive, and with large populations, it can be very slow. There are approximate methods which are much faster. One that's very widely used is what's called tau leaping. So here, instead of advancing to the next event, you move from the current time to a new time with some step size tau, hence tau leaping. For each type of event, you randomly generate the number of times an event occurred based on Poisson distribution based on the rate of that event and t. So you essentially say for each possible event, how many of these took place during this time period, and then you update all the compartments with all of those events. Now what you gain here is speed. Tau can potentially be many times the time step where two events might be, so essentially you can go much faster and essentially update as you go backwards. But what you lose is that exact ordering of events. This can be important for things like extinction events. So if you are currently at one person and you move to step size tau and you have one infected individual and you move to step size tau, and what it draws from that Poisson distribution is that two people recover, that doesn't make any sense. And you actually get a negative population in your compartment, and generally speaking, your code explodes at that point. This is also true on the other end if you have sort of a population reaching carrying capacity. If you say a ER has a capacity for 50 people, and you go from 49 to 51, what does that mean? And so this is often sort of a problem with this method, but in exchange you get much, much faster, albeit approximate results. So that's some of the sort of theory behind stochastic models. And then during the practical, we're going to cover some of the sort of implementation things and let you all play with that around with these a little bit.